Due to a recent and closely contested Twitter poll, this video is going to focus on an interesting Capture the Flag challenge write-up. The challenge involved both reverse engineering and cryptography. So by the end of this video, you will know and understand the difference between symmetric and asymmetric encryption, how to reverse engineer managed and unmanaged code, how to extract unmanaged code from a managed binary, how to create an RSA key using just the P and Q values, how to decrypt data using the openssl command line utility, and finally, how to use AES in Python to decrypt a file. So if that sounds interesting to you, let's go ahead and get started. A few months ago, I participated in a CTF which was put on by the great team over at Deloitte in the Netherlands, using their Hackazon learning portal. If you ever get a chance to use this platform, you should really check it out. Logging into the portal and looking at the challenges, you can see there was a wide variety of challenges and levels in this CTF, a number of which were way too hard for me. But hey, there's always next year. During this video, we are going to take a look at the SantaGoga challenge, which has been tagged as a crypto challenge, but also requires some reverse engineering steps too. If we take a look at the challenge and read the description, you're on Santa's naughty list, and one of your files is encrypted. Pay up, or maybe you don't have to. The challenge description fits with the Christmas theme of the CTF, but also gives a hint as to the type of challenge we are looking at here. This is likely some kind of ransomware implementation. We are also presented with 4 files, and based on their extensions, we have an executable, a PCAP, a binary file, and a PNG image. Let's download each of the files and get started in a virtual machine. Opening up the PNG, we can see a typical ransomware-style landing page. There is a fake cryptocurrency address, a countdown timer, and a message specifying that our files have been encrypted. The message warns that there is no chance to decrypt without our unique private key. So we already can start to make some assumptions here, right? Based on the other files we already have from the challenge. Important file.bin is probably going to be the flag, which has been encrypted with this ransomware. SantaGoga.exe is probably the ransomware binary, and the sock dump PCAP is probably going to be the network traffic captured during the infection. With that in mind, let's next take a look at the PCAP file in Wireshark. We can see some standard Windows noise, as well as a DNS lookup for hackyxmas.net, followed by some HTTP traffic sent to the IP address which was resolved. If we take a look at that HTTP traffic by following the TCP stream, we can see that an empty post request is sent. However, there is some interesting additional information in the HTTP headers. We can see an ID, a key, and an IV is being sent within the request. Assuming a unique IV for each encrypted file, this is probably going to be some noisy ransomware. Next, let's take a look at the actual ransomware executable file, SantaGoga.exe. Opening the binary in PE Studio, we can see that based on the rich header, the binary appears to have been compiled using Visual Studio 2017. We can also see that there appears to be an embedded SantaGoga.dll file within the binary itself. So we appear to be dealing with unmanaged code. So let's open the application up in Ghidra to start reversing. Let's start with the high-tech define strings view and search for the SantaGoga string as a starting point. Again, we can see references to that DLL file. Double-clicking on these references to follow them, we can start to get a high-level understanding of what this binary is doing. In this function, the DLL name is passed to another function, and based on that function's return value, we can see what appears to be an error code here. The managed DLL bound to this executable could not be retrieved from the executable image. So this native, unmanaged application is calling managed code from within an embedded DLL. But what is the difference between managed and unmanaged code, and why does it even matter for this problem? Basically, managed code is not directly compiled or executed as machine code. It is instead compiled to an intermediate interpreted language and executed within a managed environment. On Windows, and in this case, this is likely to be .NET executed within the Common Language Runtime virtual machine. Reverse engineering managed code is usually more straightforward, as the intermediate language can be more easily reversed by tooling back to a representative human-readable format. Unmanaged code, on the other hand, is compiled directly to machine code and executed on the underlying operating system. Unmanaged code is usually compiled and linked to run in a specific environment and is more difficult to reverse back to a human-readable format by tooling. We could see that with Ghidra, right? The decompiled representation is pseudocode-like, but we still need to invest a lot of time into reversing and understanding the lower-level functionality of the application. So how can we make our lives easier and extract the managed DLL instead? Unless the DLL is being manually mapped, the binary is probably writing the DLL to a local file, then loading and interfacing with it. I wouldn't recommend running ransomware or random binaries on your machine, but a clean CTF VM without a network connection is probably a different story. So let's just run it while monitoring our system with Procmon to try and catch the DLL as it's being dropped to disk. If we filter on the process name of SantaGoga.exe, we can start to see the operations that the binary is performing during execution. Scrolling down, we can see that the application drops the DLL to disk during execution to a temporary .NET folder location. If we navigate to that folder location, we can see the DLL we are interested in, as well as some other JSON runtime files. With a managed DLL, we can now perform the rest of our reverse engineering with easy mode enabled, by loading the DLL into a decompiler such as .peek. Under the resources section, we can see the familiar encryption warning file, so we know we're on the right track here. Taking a look at the main window class, we can also start to see the underlying functionality of the application. We can see a public key is defined, as well as the target file, which is what the ransomware would encrypt if that file exists, as well as the important file.bin file name, which is the encrypted version of the file, which we also have a copy of from the challenge. We can also see why we aren't on the naughty list too, since the important file.png didn't exist when we executed the binary, which meant that luckily nothing on disk was actually encrypted by the application during execution. Scrolling down to the send encryption key function, we again see the same public key which is used to RSA encrypt the encryption key. The function then sends the ID, encrypted key, and the IV to the hackyxmas.net URL endpoint, which we have again already seen in the PCAP dump we have a copy of from the challenge. Scrolling down some more, we can see the encrypt byte array AES function, which uses AES in CBC mode with a 16-byte block size and PKCS number 7 padding to encrypt a file. But what file? The encrypt files function is where the action happens. It reads the target file, generates a random number as a key, then encrypts the file with AES using that key. After the file has been encrypted, it sends the encryption key RSA encrypted to the external server, as well as the ID and IV, then finally writes the encrypted file to disk. The application also doesn't appear to delete the existing file. Very cool of you, ransomware. So it appears we're going to be dealing with both symmetric encryption with AES and asymmetric encryption with RSA for this challenge. So let's have a quick primer on the difference between these and how they work together in this challenge. Symmetric encryption uses the same key for both encryption and decryption. If you want to encrypt something or decrypt it, you just need to use the same key. Asymmetric encryption, on the other hand, uses separate keys. A public key, which can be shared with anyone, and a private key, which is kept, well, private. These keys are mathematically related, but if you have the public key, you shouldn't be able to derive the private key. This public key cryptography mechanism implies that any message can be encrypted with the public key, but only the holder of the corresponding private key can actually decrypt that message. Due to speed and complexity, both symmetric and asymmetric encryption are often used together. And this is exactly what is happening with this challenge too. The application is generating a random key. This key is then used to symmetrically encrypt an image. Then, the symmetric key itself is asymmetrically encrypted and sent over the network via an unencrypted connection. The idea being that if you pay for the ransomware decryption key, the bad guys can asymmetrically decrypt the symmetric encryption key and use that key to then unencrypt your files. Well, this is exactly what we want to do too, right? In order to decrypt our important file, we just need to AES decrypt the encrypted file using the IV and the key. We already have the encrypted file as well as the IV, so now we just need the key. But how can we get the key if it's asymmetrically encrypted? We would need to somehow recover the underlying RSA private key. Since RSA is a trapdoor function, this is computationally difficult. If you know the right values, it's easy to create the RSA key, as we will soon see. But going in the other direction, from the key to the underlying values in an efficient way is currently, to my knowledge at least, impossible. So what do we need? Well, to generate a private RSA key in this case, the first thing we need to have are the two prime numbers, P and Q, so that we can create the modulus by multiplying these numbers together. Then we need to calculate D by throwing around some math and Greek letters to actually generate the private key, which we can then use to decrypt the encrypted symmetric key. You can do these calculations yourself, but rather than reinvent the wheel, we can also just use the excellent RSA tool for exactly this purpose. We pass in some valid P and Q values, and the RSA tool utility can spit out the corresponding private key. But we still have a slight problem. How can we get that P and Q value? Using openssl, we can see that the public key is 1023 bits. This public key consists of the P and Q values multiplied together. So assuming these values are securely generated, this is unlikely to be something we can solve on our VM by factorization. Factorization is basically saying, hey, we have this big old number here. Can you tell me the two prime numbers, which when multiplied together equal this number? Well, we don't know those two numbers, but what if we don't have to factor the number? Maybe someone has already done that hard work for us. We can use openssl to extract the modulus, then use Python to convert that hex number to a decimal format we can more easily work with. There is a great resource called FactorDB, which, while not intuitive to use, contains a database of factored numbers, which is exactly what we are after here. So let's see if this number has already been factored by just searching for it in the database. Look at that. Lucky for us, it has been. Extracting the two numbers from FactorDB and verifying with some Python quick math, we can see that multiplying the values from FactorDB together results in that modulus number we are looking for. So now that we have our P and Q values, we can use RSA tool to create the actual private key. With the private key generated, we can now use openssl to decrypt the encrypted AES key. We can base64 decode the encrypted value, then write that value to a file, decrypt it with openssl, and output the unencrypted key in a base64 encoded format to make copy and pasting just a bit easier. So with the asymmetric encryption step out of the way, we now have all of our symmetric encryption pieces. We have the encrypted file, the AES IV, and the AES key. So let's write a quick Python script to decrypt the flag. We import functionality from the base64 and crypto packages, read the encrypted file, initialize the AES cipher in CBC mode with the IV and the recovered key, then decrypt the encrypted file, and finally write it to disk. If we open the decrypted file as an image, we can see that we have recovered the encrypted file, beaten the ransomware cryptography implementation, and retrieved the flag. Quite a nice 200-point reversing and cryptography challenge. Thanks again to the Hackazon team for putting together this CTF, and I hope to play on the platform again. If you made it this far, thanks for watching. It really helps the channel grow if you comment, like, and subscribe below. Also, if you're interested in solving capture the flag challenges across a range of traditional Jeopardy-based categories, including reverse engineering and cryptography, make sure to check out 247ctf.com.